Okay, so today we worked on practicing how to do calculations. And one of the first things I bring up is vocabulary. There is a difference between when you take qualitative data and quantitative data. Qualitative is a description. It's pink, it's red, it's soft, it's a solid, it's a liquid, all of that. Quantitative is the numbers. It weighs 0.5 grams. It's 1.6 centimeters long, and so forth. And the way that you can tell the difference in two words is quantitative has an N in it for numbers. And then this gets us into the metric system. And so the metric system, or the SI system, is our universal system we use for measuring. And we use this in science. It's based on a unit of 10. It's used in most of the world, and we use it in science. Units in the metric system, most of you are very familiar with it. Length is a meter, volume is liter, mass is gram, time is second, and temperature is Celsius. We will also be using Kelvin when we get to gas laws, and we'll talk about why we use that. So then there is this topic of scientific notation, and it's used to write very large or very small numbers. And it basically means that I'm moving my decimal. Okay? So my decimal's back here, and I need to move it to the front. 1, 2, 3, 4, 5, 6, 7. So my number becomes 1.28 times 10 to the 7th meters. I can also do this with a small number, but when I convert a small number to a scientific notation, because I'm moving to the right with my decimal, I will then end up using a negative sign to show that I moved to the right. And so again, I grab my decimal and I go whoop, 2, 3, 4, and 5. And I've got to get it behind the very first non-zero number that I see. And I end up with 3 times 10 to the negative 5. So what we did was we practiced some. So again, we're simply going to be moving our decimal. Here's my decimal. I grab 1, 2, 3. And so my number becomes 9.3653. We write times 10, and I moved it 3 spaces. Let's repeat the process with number 2. So I have 7.120 times 10 to the second. Repeat again with the next number. 1, 2, 3. Now, number 4, 5, and 6, we're going to move in the opposite direction. Remember, we want to get it to the very first non-zero digit. So we need to move this decimal behind this 2, and then we're done. But since I moved it the opposite direction, I now had to put a negative sign up there to show that it was a small number. And here we go again. 1, 2, 3, 4. 8.22 times 10 negative 4th. And the final one. 1, 2, 3, 4, 5, 6. 4.77 times 10 to the negative 6. And that's scientific notation. So then we discussed sig figs, and sig figs just refers to significant figures, and we can only record to our least precise measurement. So if we're measuring something and it only goes out to 1 decimal, then I can only record 1 decimal. Okay. It just gets into the fact that it's when you're adding on any numbers past what you know of, the next digit is considered to be an estimated digit because we're not 100% sure that's what the number is. And so significant figures just tells us the specificity of which we measured. Now, there are rules for our sig figs, and you can read over those. Non-zero digits are always significant. So 4, 7, 3, 5, always significant. Zeros before other digits are not significant. So we call these leading zeros, and those are not significant. Zeros between digits are significant. We call these captured. So if they're captured between a number, then they are significant. Zeros to the right of all other digits are significant because they're to the right of the decimal point. And the key thing is the decimal point here, because it is assumed that if we put it down, we measure to that level. And it's impossible to determine whether zeros to the right of the other digits are significant if the number has no decimal point. So if it's not there, then we're not 100%. We think it's about 8,700 kilometers, but we're not 100% sure. So that's why those zeros are not significant. If a number is written with a decimal point, zeros to the right of all other numbers are significant. So again, we're getting to the decimal point. If you put a decimal point down, then everything to the right of that decimal are significant. And all digits in the coefficient of number written in scientific notation are significant. So let's look at this. So I have 9269. All non-zeros, all significant. So there are 4. The next one, number 2, I have a captured zero, which means all are significant. Number 3, I have another captured zero. All are significant again. 1, 2, 3, 4, 5. Now, this time, I have this zero that is captured. But these zeros at the front, they're just placeholders. Because I can change this and make this 4.02 times 10 to the negative 2. Which is why I only have 3 significant figures. Let's look at number 5. This leading zero is not significant, but this zero is significant. And once again, here we are measuring, so those 2 are significant. Those of you who are in honors, I do expect you also to do this. So I'm going to go ahead and put this down. There's 3 here. These are the only ones that are significant here. All significant. Notice this one, we're missing a decimal. So technically, those are the only ones significant. No decimal, but these zeros are captured. That's a 4. Now the difference between this could become 1.09 times 10 to the 4th. Okay. Here's where I'm significant. This front part's not. This time I've got a decimal. So the whole thing is significant. Okay, calculations with sig figs. This gets into the rules for it. Basically, if I give you a decimal, you give me a decimal back. And that's what it's going to come down to. Okay? And I'll be looking for your sig figs as they come through on that. These are some rules on addition. Now, density. So density compares the mass of an object to its volume. And its mass is substance divided by its volume. So I can do either I can do grams per milliliter, or I can do grams per centimeter cubed. Okay? Note that 1 milliliter equals 1 centimeter cubed. This is just a chart of common substances and their density. I will note here, you are expected to know that water's density is 1. So anything less than 1 floats, anything greater than 1 sinks. All right, so then we did some problems. So I have a block of density. And it occupies a volume of 15 meters, 15.0 milliliters, is that right? And it weighs 40.5 grams. Now, I do expect you to write your units and label. We have no naked units, so take your time to write it. That's how we double check ourselves to make sure we have them in the right spots. And when I perform the math here, I'll get 2.7 grams per milliliter. Problem number 2. Mercury metal is poured into a graduated cylinder that holds exactly 22.5 milliliters. The mercury is used to fill the cylinder that weighs 306.0 grams. From this information, calculate the density of mercury. So my mass, again, same formula, is 306.0 grams. My volume is 22.5 milliliters. And I get 13.6 grams per milliliter. Question number 3. What is the weight of ethyl alcohol that exactly fills a 200 milliliter container? The density of ethyl alcohol is 0.789 grams per milliliter. So once again, we're starting with the same formula. Density equals mass divided by volume. It just happens that this time we're solving for our M. So 0.789 grams per milliliter equals X over 200. So I need to multiply 0.789 times 200 and I get 157.8 grams per milliliter. Final problem. Same formula, density equals mass times volume. It just happens that this time the volume, so I have this rectangular block. It weighs 1896 grams. The dimensions of the block are 8.4 by 5.5 by 4.6. That's your volume. So I need to do a pre-calculation here. I need to take the volume is 8.4 times 5.5 times 4.6. When I do that, I'm going to get 212.52 centimeters cubed. Now I have everything I need. Back to density equals mass divided by volume. My mass is 1896 grams. My volume is 212.52 centimeters cubed. And I perform my calculation. And I get 8.9. Now, I think that's a great answer, but it's not right. And it's not right because my grams was given to me and there's no decimal here. So, just round this up. It becomes 9 grams centimeters cubed because I can only be as precise in my least precise measurement. My least precise measurement doesn't have a decimal, so I can't record a decimal. And that's what we did today in class.